Good afternoon. We fixed this. I'm Tim Wickberg. I'm the CTO for SchedMD. We're the makers of Slurm, talking especially about stuff Praveen from Google has been working on with us for a while around Topology-Aware CPU scheduling, using the DRA subsystem to get this implemented. I'm going to try to key up sort of some of the requirements and why this is interesting. I will admit I am not a Cube developer myself. My team does not trust me to do Golang because it looks terrible. I'm actually a C developer by trade. But from Slurm as a traditional HPC workload scheduler, we're trying to bring some of the same kind of concepts over to be able to manage a lot of sort of HPC AIML style workloads a little more efficiently in the way that the HPC community has over the years. So the talk's broken up roughly in 5. We are going to ask folks to hold for questions till the end, especially so Praveen has plenty of time to run through a demo he's got prepared. We tried to get an unconference session to kind of carry on some of this after there was some confusion there. We've been told we are okay to have an unofficial unconference session outside after this. So we're happy to carry that discussion on out there, especially if questions run long. So Kubernetes resource requests as they exist today. We have very broad requests for CPU and memory as part of the pod specs. Then we have the DRA model, which is over on the side, doing more dedicated resource allocation for things like GPUs and NICs. Native resources have this very coarse capacity check. The Kube scheduling interface is working sort of at a very abstract model of resources within the nodes, especially in the CPU and memory realm. It's not trying to deal with the actual hardware that is in those compute nodes. Any of those decisions is being delegated down to the kubelet to finally do that binding for the workloads at a much later stage, not at the central scheduling step. This has a lot of unfortunate ramifications. Because nothing is centrally planning this, there's this inherent disconnect between what the DRA subsystem is going to do in terms of placement for GPU and NIC resources versus what the kubelet may eventually do when the application runs onto the node, and in terms of what CPU resources are available to that same application. This misalignment here represented as a disconnect between the CPU over on one side, but the GPU is actually on a PCIe complex anchored over onto a different set of cores, is very detrimental to a lot of workloads, very catastrophic for performance for quite a lot of more finely tuned applications. So the split brain comes about because the Kube scheduler does not know what that topology, especially the CPU topology, looks like within an individual compute node. And then the kubelet topology manager doesn't look at what DRA's got, that doesn't know how to sort of reconcile these two different representations of compute resources built within the compute nodes. Sorry. Again, trying to cover the motivation here. These AIML, HPC, Telco workloads do care about this alignment a lot. If you have a GPU, you want CPUs to be allocated to you directly adjacent to them. If you have this misalignment, applications will suffer from it. But within the current stack, there isn't really a way to satisfy these resource constraints. That's what we're trying to cover with this idea of a CPU driver for DRA. This is just a few sort of benchmarks we've seen floating around there where these misalignments do stack up, are very measurable in terms of application latency, response time. The HPC space, the traditional high-performance computing environments, this is something they've been working on for decades and have even finer-grained requirements and directives around. This 10% latency is a very kind of high-level stat for what can happen. There's very specific applications I can point to where it's even worse, 30, 40% performance differences on misaligned versus aligned resources. There is also, we did want to call out, there's another talk looking at some other ways to accomplish this Thursday, achieving peak performance through hardware alignment and DRA, kind of carrying on some of this motivation. Beyond that alignment, from the kubelet's view, everything is treated equally. There is no way currently to talk about, hey, I want CPUs on specific sockets, specific NUMA realms, specific L3 caches, and I want to dedicate those exclusively to this resource. and align it at the same time with the GPU. So again, more of this motivation is, without this alignment, there's a lot of workloads that just don't port well into the cube stack as it exists today, especially from the HPC space. HPC workloads can go even further in how they want to lay out multiple processes, not just a single process. They want to say we want to round robin them between sockets. We want the socket layout to look like this because this represents some internal communication structure that we've built into the application. Here's how this all ideally should look. And as a subset of Slurm's own allocation tools here, there are dozens of flags that give users of that stack very fine-grained control over where stuff lands that don't have an equivalent in the cube stack today.
So for the second part of this presentation, we are going to look into like how we can solve like some of these disadvantages that like Tim was talking about by using like DRA for native resources. So the core idea here is like DRA, along with being like a powerful API for requesting and managing resources, is also like a very flexible way to make very precise requests for like native resources like CPU and memory. And the CPU DRA driver is like the open source project that we've been working on, which is like a first step to address this, starting with CPU. So yeah, like we have a repo in Kubernetes 6, which kind of looks at this problem. The way to use this is like pretty straightforward, like very similar to any other DRA driver. We install this as a daemon set on the cluster. But the main prerequisite to use this DRA driver is like we would need the kubelet static CPU policy to be disabled. The main reason behind this being like in kubelet today, if we have the static CPU policy, like kubelet manages the C group settings for like CPU pinning. And with the DRA driver, we kind of take over the responsibility from kubelet and do this management within the DRA driver. And like basically, we would not want to have like multiple, like 2 different components owning this C group management. So yeah, like once the daemon set is installed, it starts publishing the CPU resource slice. Currently, like we only manage like guaranteed CPU requests through the resource claim. So when I say guaranteed, like it means basically we manage CPU requests only for workload that needs like CPU pinning, and for like rest of the workloads which are okay with like sharing CPU with other like jobs running on the node, we can continue using like the regular way of like requesting resources through the pod spec. Yeah, like once a daemon set, the CPU DRA driver daemon set is installed, it basically scans through like the topology on the node, and it starts publishing the resource slice. So here is an example resource slice that we have. So in this case, like each CPU is represented as a device, and along with the CPU, we also have like rich attributes which exposes a lot more like finer details, like CPU ID, core type, L3 cache, and so on. So depending on the hardware, the underlying hardware, we could essentially expose a lot more like micro topology of the node, like through this resource slice. And basically, this would enable like scheduler to have a view of like micro topology on the node, and the users can like would be able to request them through the regular like DRA resource claim API. So yeah, this may not be or need not be like the only way to model CPU. In not all use cases would need like this amount of information. So we could always have like different types of modeling which can be enabled through like DRA features like consumable capacity. So in this example, like we have a resource slice where we just expose like a socket ID and the number of CPUs available in the socket. So basically, this would mean like lesser number of devices and is more like scalable for larger clusters as well. So yeah, this is the resource slice part. And coming to how this all works on the node, uh, if you see the block on the right, the orange block, that is, there are like two components on the CPU DRA driver. One is like the Kubelet plugin, which interfaces with the Kubelet and handles like all of the DRA requests. And the second one is the NRI plugin, like the node resource interface plugin, which basically provides like a pluggable interface with the container runtime and is responsible for like all of the actuation. So if we can just walk through like one pod as an example that lands on the node, like basically if we have a pod which requests CPU, in this case like we are requesting 20 CPUs through the resource slice. Once it lands on the node, the kubelet will look at the resource claim and basically make a call to the DRA kubelet plugin. And in the plugin, we look at the resource claim, and the kubelet plugin will generate like a CDI file, like which is basically like a handover mechanism between like the DRA kubelet plugin and the rest of the container runtime and the NRI interface. So once like kubelet once the kubelet plugin creates the CDI file and passes this back to kubelet, so when the container is being created, so basically when kubelet is making the create container call, it adds this CDI information and passes this to the container runtime. And like the last stage is the container runtime, if it has the CDI like ID, it calls this NRI plugin, which looks at this and does the actual enforcement. So basically, this decides like, not decides, this enforces the C group settings that goes on to the container like when it starts running. Yeah, so for the next part, I had a demo. So let me see how I can make this work with the mic.
Get the demo up.
Maybe I can just keep it here. And, okay. So thank you so much. So yeah, so basically in here I have like a cluster which is running GK1, like Kubernetes 134, and here I have like 3 different node pools. Like one of them, I mean, there are 2 node pools which uses GPU, and one of them is the. Oh, sorry. Is it better? Okay, thanks. So yeah, like we have 3 different node pools. 2 of them have like GPU machines, and one of them is the default one. We can just ignore the default node pool for now. So if I've also SSH'd into the node, like on the top. So if we look at the topology on the node, I think I ran this before. So I hope this is visible enough. So basically, like, this is a GPU node which has like 8 GPUs in total, 4 GPUs on each NUMA node, and it also has like 8 RDMA NICs and 4 again on each NUMA node. So GPU 0 to 3 are on NUMA node 0, and GPU 4 through 7 are on NUMA node 1. And along with like this, like each NUMA node also has like multiple PCI switches. So here GPU 0 and 1 and NIC 0 and 1 are on a single PCI switch. So what it means that like the data path between these devices are going to be like most optimal. But if GPU 0 has to reach like a NIC on a different NUMA node, it has to cross through like the inter-socket communication like between the NUMA nodes. So yeah, this is the topology on the node. So on this cluster, I also have like the NVIDIA DRA driver and DRA net pre-installed. Sorry. So I can close the top part now. So So I have DRNet installed on all the nodes. I have NVIDIA DRA drivers installed on the 2 nodes which have GPUs, and they all are like already publishing resource slice. So yeah, this is, yeah. These, like we have 2 resource slices for GPU and 3 for DRNet. So now I'll just install like the DRA CPU driver. So this installs a daemon set, and basically if I see it, yeah. So now we also see, along with other devices, we see like DRA resource slice which is being published on the node. So one thing I missed mentioning was, like, if we look at the if we go back and look at the nodes again, so on one of the nodes which says static CPU, I have enabled like kubelet policy, static CPU policy, and the other one, it does not have like kubelet static policy. And basically the DRA CPU driver, it only runs on the node which does not have kubelet static policy enabled. So now let me install like 2 representative like HPC workloads. So yeah, I created both. So let's also look at like one of the resource slice while this pod starts up. So if we look at this resource slice, so basically we have like all of the CPUs listed with all of the attributes. And what I'm trying to do here with these 2 workloads is, like, on one of them, HPC workload 1, I only have like NVIDIA DRA like request and RDMA NIC, and I'm also requesting like both of these devices should be on the same PCI route. And on the second workload, along with GPU and NIC, I've also added the CPU request, like requesting for 20 CPUs and a specific core type. I've also specified like align, along with GPU and NIC alignment, also align CPU and RDMA NIC. And I'm also requesting all of the CPUs from the same L3 cache. So basically a bunch of requirements on the CPU side. And rest of the pod is like, basically we have a resource claim. And currently we also need to make the request that we do through DRA, also through like the standard pod request to make the allocation accounting work. But this is something that like we are working to like be able to not do this. So now we should have, we should have like both the pods up. So yeah, both the workload pods are running, one of them on the static CPU node and one of them on the other node. I wrote a simple script which basically execs into the pod and like scans through all of the resources allocated on the pod. So what this shows is like this workload 1 is assigned like 20 CPUs from NUMA node 0 and like L3 cache 0. It is also assigned 2 GPUs and 2 NICs from NUMA node 1. So this is with the standard like kubelet static policy. Now if we look at this, like the workload with DRA, the one difference that we should see is like here we have CPU from node 0 and rest of the devices from node 1. So if we look at workload 2, like the DRA driver takes control of CPU assignment. So now we have like CPU from NUMA 1 and rest of the devices also from NUMA 1. So yeah, this is basically like DRA CPU driver working in action. So yeah, that's about the demo. Thanks, Tim. So yeah, I think the use cases I covered like through the demo itself. One of them is resource alignment. One of them is like we can make fine-grained requests like specific cache ID and so on. The other new like requirement that we have come across is like with the prioritized list DRA feature, we can now, we would be able to say something like, hey, if a cluster has like 1 GPU, give that. Otherwise, I'll take like 20 CPUs. Or even within the CPU type, we can say, like, give me 20 performance cores or give me like 40 efficiency cores, like whatever is available on the cluster. So these are some of the use cases that can be enabled by DRA for native resources. So yeah, coming to what we are currently working on. So basically, the main thing that we are working on now is we now have like 2 different ways to request for like the same native resource. One is through DRA and one is through pod spec. And we need like some form of coordination between all of the existing mechanisms on the kubelet and on the kube scheduler to work along with DRA to make sure, like, one, the accounting of resources is done properly. And also on top, like other than accounting, like we currently rely on the standard resources for a bunch of things. Like there are a lot of downstream things like QoS class, eviction, preemption, and a lot of things which are still based on like the native resource request. We have an enhancement issue where this has been like discussed even more, and this is something that is yet to be solved. There is also a need for like more standard attributes, like for, say, NUMA or sockets, so that devices have different ways to align. About these topics, there is, if you're interested, there is a meeting scheduled for next week, and you should be able to find this in the device management working group. Some more things are like we should have, like with newer DRA features, we would have more ways to model the topology on the node. Like consumable capacity is one of them that I just showed. Like there are more things that could be done with like DRA partitionable devices and so on. And like most of the current talk was focused on CPU, but similar things can be done with like other resources like memory and huge pages as well. I know that like there is one project in a POC which is in progress to explore using DRA for memory. So yeah, these are some of the things that we've been working on. So this is like, there are a lot of active discussions that are happening around this, and this is again like the repo if you want to like try it out and give us feedback on this. Yeah, this is everything I had for the session. Any questions so far?
If you can come over to the microphone.
First, I have one small question. So you mentioned that we have some alignment issue at the beginning. So we said let me find the slide. Oh yeah, here. So the topology is non-deterministic during scheduling. So can you explain a little more about that?
Are you talking about like
beyond alignment?
Oh, sorry.
Yeah.
This one?
Here, yeah.
So yeah, I think like this one is, the top view represents like what the scheduler or the kubelet currently knows about that micro topology on the node. It considers, like, it knows about sockets, and it treats all the CPUs on the socket as basically like the same thing. But if you look at like a real machine, it could have like if you see the bottom diagram, like there are multiple L3 caches within a NUMA node, and there are different types of cores like efficiency cores, performance cores, and HPC or like high performance workloads would want to be able to specify like not just give me 5 CPUs, it should be able to specify like give me 3 high performance CPUs on a particular cache and things like that. So,
gotcha. So basically, you mean the capacity is static, but the available resources are dynamic.
The available resources are also static. The problem right now is like Kube scheduler does not have a view of like what is actually available on the node. So it does like a coarse grain resource allocation. So basically, it knows like how many CPUs are free and how many are used, and based on that, it will schedule workload. But DRA allows for more specific kind of requests.
Gotcha. My second question is that I think DRA might bring some fragment. So have we considered a live migration? So we migrate some workload from here to there so we can increase the utilization.
Yeah. I think like that's a good question. So specifically, like if we start exposing each CPU as a device, fragmentation is definitely a problem. So if workload starts saying like, give me CPU 2, 3, 4, and other workloads may not know about this, yeah, like one way to avoid this is basically, if we don't need that level of granularity, we can have like socket level granularity similar to kind of what Kubelet has. Like in this model with consumable capacity, we just expose like we have 2 sockets and each of them have 32 CPUs, and internally within the DRA driver, we can like manage the fragmentation problem. Like basically we can allocate contiguous blocks of CPUs whenever possible.
Yeah, also have we considered the live migration? For example, I have 2 training jobs. I might want to migrate the job from node A to node B to defragment. Maybe it has many.
No, I
Okay.
don't have a good answer for that right now.
I mean, it's not something we've really looked at yet, but in general, I mean, that's kind of a general problem with a lot of things we're doing, and there's also preemption and things like that. So we don't have like a defragger planned right now. But the other point I wanted to make, and maybe Tim, that one of the goals here was to enable tools like Slurm, which have been doing this for many years and understand how to lay out things, to have the APIs available to them to provide the instructions for Kube Scheduler and Kubelet and everything to just do what they tell them. And so that's an alternative solution to that problem is, well, maybe that's beyond Kube Scheduler's capabilities, but you hand it off to something like Slurm.
So to build off of that, I'm not proposing, I don't think we're saying that this is meant as a direct pod-by-pod API that they should be directly trying to micromanage. My request and sort of where we get involved is for us as somebody playing in the scheduler space to have the plumbing for the scheduler, in our case it's our Slinky Slurm bridge, be able to communicate this very directed placement requirement to the kubelet and to the runtimes and have that enforced. The fact that you can come in and do some of the CEL selection is sort of a side effect of how DRA represents and is built into the rest of the ecosystem. But I think for workloads, there need to be a set of higher level requests to say, I just need 4 CPUs and I need them to be allocated in proportion to the GPUs and to the NICs, get all of this alignment to work, but the user shouldn't be having to construct a full CEL syntax to try to do all of that. I think that's asking too much from them. And that's where my slightly opinionated stance is that this should be internal plumbing within Kubernetes, but not necessarily the API to the end users. Okay, nobody's lynching me yet. That's good.
Does it go beyond the topology? For example, if you wanted 2 isolated CPUs?
The intent here is that these are isolated. I didn't cover this as much. HPC workloads assume static, isolated allocation of CPUs. They're not expected to interleave other workload, and that's where coming from the HPC space into the Kube space, one of the biggest disconnects for me has always been this idea of millicore CPU allocation, where you're just fighting with the Linux kernel scheduler to get your CPU time. For workloads that are compute dominant, having that workload getting moved around between different cores on the node, between different L3 caches, different affinity to the GPU and other devices is antithetical to the way the HPC industry has thought about this for decades. So this in part is meant to give us, from the HPC side, a way to do that same type of control we're used to. And that's where me and my team kind of got involved in this whole project.
So does that mean it's actually using the isolated configuration from the host itself. So if you wanted to isolate 4 cores rather than all of the cores.
I believe this is.
This would specifically pin like 4 cores and nothing else like would be able to run on those cores.
Yeah, but the host, the kernel threads would still run.
Right now, no. Like basically, the kernel threads do not have. I mean, it's not isolated, but that is something like we've been actively like.
Yeah, because that's something we use on my project, where we do recommend running on isolated.
Okay.
Otherwise, there's potentially quite a big performance loss.
I think that is. I'll take that as a feedback and like follow. Thank
I was
you.
going to say, at least for what we do with our scheduler plugin, that's implemented through something called core specialization, where we can fence off stuff. Because the HPC space has seen that same problem of kernel threads, like file system, especially file system. Weka IO is really notorious for this, of needing to be isolated to not trash all the other threads on the box.
So the other thing we can do is, so one of the other things in DRA is that we don't use yet is on any resource claim you can attach config. So that's just, it's an arbitrary thing that's driver defined, like it's just a structure. And so any kind of additional isolation requirements or specialized things that aren't exposed like as an attribute and a selection criteria, but they're more configuration, can be put in there. So that's where that can be put.
So if you use this today with a kube scheduler without another external scheduler like Slurm, is the device Dynamic Resources plugin able to search for a preemption if a higher priority resource comes in requesting a slice and then it's all used by lower priority? Or is that seems like that's complex with so many ways to request. So what's the state of that?
I think that is one of the things that we are like trying to address with like this enhancement issue. Like basically right now QoS class is what decides like preemption, and that the DRA resource request does not directly affect the QoS class. So right now, no, like it does not have a bearing on the order in which like the workloads are preempted, but that is one of the things being discussed on this enhancement proposal.
I think it could be a good idea as we're transitioning from the classic like node, what is it, resources? What is it? What do you call the custom? Extended resources mode to like full DRA mode, that we make it clear to administrators, like when you make this shift, when you choose to use this driver, you now have advisory requests, but you do not have the type of fully working scheduling that you expected before. So I'm not sure what the language is for that, but I think we should make that more clear as we ask people to make that transition.
Yeah, I think, yeah, that makes sense.
I had one question, but before I asked that, you said something like using Slurm as the scheduler. Does that mean just like making the Slurm task plugin kubelet or something? Is that kind of what you mean? Like rather than cgroup, you know?
No, this is something, we have a presentation, I think it's Wednesday, on what we call the Slurm Bridge, which is Slurm as a scheduler plugin to the Kubernetes stack. So workloads still stay within Kubernetes. Sorry, I know we're just about out of time. If you guys don't mind moving the rest of the questions out to the hallway, I want to be respectful of the next session coming in here in a minute.
Okay.
Thank you guys.
Thank you so much.